Hi, my name is Sanghyun Cho, and in this video, I will give brief overview of my project on steady-state visually evoked potential implementation in brain-computer interface. Brain-computer interface, in short BCI, is essentially a communication channel between human brain and computers. Electrical activity in the brain is transduced into digital signals to interpret user intention. Unlike a typical user interface, which requires physical and external inputs such as keyboards and mouse, BCI measures the electrical activity of the user's brain using non-invasive EEG headset. BCI can recognize certain brain activation patterns, which can be associated with executable commands. Steady-state visually evoked potentials, or simply SSVEP, is brain signals that are natural responses to repetitive visual stimulus with user-defined frequencies. When human retina is excited by visual stimulus in frequency range 3.5 Hz to 75 Hz, the brain generates electrical activity with the same frequency of the visual stimulus. This visual activity is usually recognized in the occipital lobe of the brain, which is located at the back of the head. Multiple light sources can be used as repetitive visual stimulus: LED, CRT, and LCD. LED is the most frequently used because it is readily available and induces the strongest brain response. There are two types of RVS. Complex RVS is essentially rapidly changing visual patterns, as illustrated in the alternating checkerboards on the right side, whereas simple RVS involves nothing but a flickering light source at a specific frequency between 3.5 to 75 Hz. My contribution of this project would be using different colors to observe simple RVS and test if it causes different yet recognizable brain activities. The purpose of using color modulation is to increase the number of commands available in the limited frequency range. Different colors result in different power spectra despite using the same frequency. Also, using different colors could reduce the risk of photosensitive epilepsy, which is a type of seizure induced by flickering lights. Inside the source code, I have provided a Python implemented console where you can change the visual stimulant of a circle with different colors and frequencies. There are different types of SSVEP methods. First method, canonical correlation analysis, is widely used in spatial filtering method that uses sinusoidal signals as reference signals. It is popular because it can detect SSVEP signals without calibration. Continuous wavelet transform acts like short-time Fourier transform, but varying window sizes based on frequency. We use power spectral density analysis, which uses autocorrelation function of the signal to calculate the power spectral density. It converts from time domain to an energy distribution in the frequency domain. And here we have a quick MATLAB demonstration where we have the EEG signals from the 8-channel headset, and we extract certain intervals from all those signals, and we extract them into epoch. And using these epochs, we get the power spectrum of the EEG signals by using fast Fourier transform. And it continues. Since EEG signals are always contaminated by different artifacts and random noises, it is necessary to filter out the unwanted noises. We use FIR bandpass filter to limit the frequency range, moving average filter to reduce the white noise, which can decrease variance of the signal at the cost of resolution. Finally, the baseline estimate from the data was removed. Here is the overall system we implemented for this project. Brain activity of a user looking at visual stimulus is measured through BRI 8-channel EEG headset. Epochs were selected as specific intervals, and the filter out signals were mapped to frequency region by using fast Fourier transform function in MATLAB. The features like relative amplitude and frequency are extracted from power spectral density graph. The resulting feature vectors are processed through the artificial neural network, which I trained using datasets I collected. As for the machine learning method that I use in this project, one could use linear discriminant analysis to obtain a plane in vector space that successfully separates and classifies the input vectors. However, I used fully connected layers without convolutional layer or pooling layers since the feature vectors were so very simple. As for the result, I was able to classify frequency at about 90% accuracy, which with the best performance at around 15 Hz. Red color had the highest score with 72% and the blue with the lowest at around 50%. Thank you so much for watching, and here are the references that I used.